Welcome to Physics 141 Online. In this video, I'd like to give an overview of the properties of vectors and then move right into one-dimensional motion by defining average and instantaneous velocity and acceleration, and then showing how to get equations that are useful for describing one-dimensional motion with constant acceleration. And then we'll finish by talking about the special case of objects that are falling freely near the Earth's surface. Preliminary information deals with an important topic that you will use in almost every assignment this semester, and that is dealing with units and making unit conversions. So I'll just give a very simple example of showing how you can take quantities in one set of units and convert them into another, often more useful set of units. It also illustrates the need to carry units along in any kind of calculation of physical quantities that we do. So here's an example. The Earth has a radius of 6,370 kilometers, which is what you'll find if you look in the back cover of your textbook, and we're asked to find the speed in meters per second of a point on the equator as the Earth rotates. And so we just have to remember that speed is defined as distance traveled divided by the time it takes. So for a point on the equator, the distance it will travel in 1 day will be the circumference of the Earth, so that's 2 pi times the radius, and the time is simply 1 day. We just know that from our everyday knowledge. But if we were to calculate the numbers, we would find the speed in kilometers per day, and we want to know what it is in meters per second. We accomplish this by multiplying this answer here by various unit conversions. And a unit conversion factor is a ratio where the quantity in the numerator and denominator are actually the same quantity, just expressed in different units. So for example, I want to get rid of kilometers in favor of meters. So I need to use a conversion factor that has kilometers in the denominator and meters in the numerator, because when we multiply this out, the kilometer factors will cancel, leaving behind meters. And I know that there are 1,000 meters in 1 kilometer. So that's my conversion factor that will get rid of kilometers in favor of meters. However, if I stop here, I'll have an answer in meters per day. So what we have to do now is get rid of day in favor of, eventually, seconds. So I know that there's 24 hours in a day. So the conversion factor I need is 1 day divided by 24 hours. Again, I know that it has this configuration because I want day to cancel out in favor of hours. Now I can go from 1 hour to 60 minutes, and then finally 1 minute is equivalent to 60 seconds. So if I treat the units as algebraic quantities, kilometers cancels, days cancel, hours cancel, and minutes cancel, leaving behind an answer in meters per second. So please get in the habit of writing out these unit conversions in all of the calculations that you do that involve numerical results. All right, now a vector can be contrasted with a scalar. A vector is a quantity that has both magnitude or size as well as direction. A quantity, by contrast, that has magnitude but no direction is called a scalar. And here are some examples. Scalars are quantities like mass, temperature, and volume, whereas vectors inherently involve direction, velocity, acceleration, force, and momentum. Graphically, we can describe a vector as an arrow. The vector's direction is obvious from the sketch because it goes from the tail toward the head. The length of the arrow is used to represent the vector magnitude. The longer the arrow, the larger the magnitude. So if this were a velocity vector, the faster the object's moving, the longer the arrow would be. But we often want to be able to do analytical calculations, especially those involving numerical quantities, and we might want to add two vectors together. For example, if the two vectors represent physical displacements, we'll want to add them together to get the net displacement. So here we draw our vector A with the tail at the origin, And we can see that you can get from the tail of A to the head by first traveling a certain distance along the x direction, and then by turning and traveling a certain distance along the y direction. And these two amounts are referred to as the vector components of A along the x and the y directions. And we write this down. First of all, we can see that trigonometrically, if the angle theta is the angle that vector A makes from the positive x-axis, we can see that AX is simply the magnitude of vector A times the cosine of theta, and AY is the magnitude of A times the sine of theta, remembering that what we have here is a right triangle. Then, in addition, we can write down the vector A using what's called unit vector notation. The quantity I hat and j hat, those are vectors that have length 1 and that lie along the two coordinate axes. So I, or I hat, is a vector of length 1 that lies along the x direction, and j hat is a vector of length 1 that lies along the y direction. And so A, according to this formulation, the vector A is defined as traveling a sub x distance along the x direction, and then a sub y distance along the j direction. And that's a very handy way of writing down that vector. Now, as I said before, the reason we might want to do this is if we want to add or subtract vectors from one another. The graphical method of showing how to do this, which is often useful if you want to just get a rough idea of what the answer should look like, is accomplished using the head-to-tail method. So if we want to add vectors A and B, we take the head of A and connect it to the tail of vector B, and then the sum of the two vectors, what is the resultant of having vector A and vector B put together, is the vector that leads from the tail of the first vector to the head of the second vector. That's A plus B. Conversely, if we want to subtract two vectors, subtraction is really adding the opposite, so that A minus B is what you get if you take the B vector and flip it backwards to create negative B. So A minus B is A plus the opposite of B. And here you can see the result. Analytically, this is going to be the method that we will choose to add or subtract vectors if we want to get numerical results that are quantitatively useful. And the basic rule is that the sum of two vectors is the sum of their components along each of the two, in this case, two coordinate directions. We could, of course, have a three-dimensional situation. So vector A plus vector B, if we know the x components of the two vectors, we simply add them together, and the same thing with the y components. So we could get a numerical value for the sum in this way. Now, let's launch into kinematics, which is the study of motion. To do this, we will define displacement, velocity, and acceleration, and show how these quantities are related to the time it takes an object to move along the x-axis. So these formulas we're going to write down are strictly for one-dimensional motion. The average velocity in the x direction, since that's the direction that the particle can move in, is defined to be the change in the x-coordinate divided by the change in time. Delta always means change, and it's always defined so that delta x means the final x position minus the initial x position, and the same thing with time. The 3 bars here means that this is a definition. So that's the average velocity. Now we will eventually show how to calculate the instantaneous velocity, which is, of course, the velocity that the object has at a specific moment in time. The average velocity is the velocity it has averaged over an interval of time. But instantaneously, how fast is an object moving right at one instant in time? That's accomplished by using this definition delta x over delta t, but making the interval of time that we use to do the calculation smaller and smaller until it reaches a limiting value where delta t becomes so small that it essentially vanishes. And using what's called limit notation, we write down that the instantaneous velocity along the x direction is this quantity delta x over delta t in the limit where delta t becomes 0. And symbolically we write this down as dx over dt. And we'll show how to do this calculation a little bit later, but this is called a derivative. And a derivative, we would say this is the derivative of the position x with respect to time. The graphical meaning of the derivative, or the instantaneous velocity, is that it's the slope of the position versus time graph. Similarly, we can define average and instantaneous acceleration. Along the x direction, the average acceleration is simply the change in the x component of velocity, right, the velocity along the x direction, divided by the change in time. And we can also define an instantaneous acceleration, which would involve this limiting notation, where we would take the average velocity, and in the limit where the time interval is small, then we get what is the particle or the object's acceleration at that particular instant. And notationally we write this down using that same kind of notation, except now instead of dx over dt we write dvx over dt, and we would call this the derivative of vx with respect to time. Graphically, once again, this instantaneous acceleration is the slope of the velocity versus time graph. So with those definitions, we can now move on to write down the equations that describe the motion of an object in one dimension with a constant acceleration. And we will see why this is a special case that's useful. It is a special case. The equations that we get here will not apply to all situations, but anytime there's an object moving with constant acceleration, these equations will work. So if the acceleration along the x direction is constant, then we can take our definition for the average acceleration and write out, of course, delta Vx is going to be the Vx final minus the V0x, which would be the initial velocity, divided by the change in time, the final time minus the initial time. We use 0 here to indicate the initial values. And if the acceleration is constant, then we can just write down that this is a sub x, the x component of acceleration. We don't have to say it's average, because if the acceleration is constant, the average value is equal to simply the acceleration itself. So now what we can do is let the initial time be called 0. We'll just say that we start the stopwatch at the initial time, so we'll call t0 0, and we can solve for v sub x. So the first step would be to realize that if t0 is 0, we multiply both sides by t, and we get vx minus vx0 is equal to, actually that should be v0x, my fault there. It's equal to ax times t, and if we solve for vx, we get vx equals v0x plus axt. Very simple, right? This is important because it shows us that if we know the original velocity, v0x, and we know the time and we know the acceleration, we can calculate any final velocity at any instant in time. Graphically, constant acceleration motion means that if we make a graph of vx versus t, it's going to be a straight line with a constant slope, which by definition has a constant slope. So this equation vx involves t as the independent variable. So if we plot vx versus t, we would get a straight line where the y-intercept, the value of the velocity at t equals 0, would be v0x, and it would have a straight line where the slope is equal to a sub x. Remember, we know that it looks like this because the general equation of a straight line, y equals ax plus b, where a is the slope and b is the intercept, this has the same form as what's shown up here in the red box, except the variables, instead of being y and x, the variables are vx and the time t. So the fact that that's a straight line is no surprise. Now let's go one step further. We can use this same graph to find an expression for the position of this object as a function of time. How do we do this? Well, we know that the area or at least we can argue, we can show that the area under the v of x versus t graph, starting at time t equals 0 to some later time t, is simply the change in the position. The change in the position is the area. The reason we know this is if this line for Vx versus t were just horizontal, if the velocity were constant, then the displacement would simply be the velocity times the time, right? So that would be the area underneath that curve. And so it's a very simple extension of that argument to say that if the velocity is changing, then the displacement that the object has from some initial time to some final time is simply the area underneath the velocity versus time graph. And so we're going to do that here. We're going to write down what that is by taking this linear velocity versus time graph and calculating the area underneath it from t equals 0 to a final time t. So we take that shape and break it down into a rectangle and a triangle. And we know formulas for how to find the area of a rectangle and the area of a triangle. The only thing that we really need is the height of the triangle. That's easy because from the formula, Vx is V0x plus AXT, so that additional amount AXT is the height of the triangle. And now all we have to do is write down that delta x, the area underneath here, which is how far the object has traveled along the x direction, it's equal to the area of the rectangle, which is simply V0x times t, plus the area of the triangle, which is a half times the base times the height. So 1/2, the base is simply the time t, the height is AXT, so we multiply those two together and we get that delta x is V0xt plus 1/2 AXT squared. We can also write this, instead of delta x, we can call this x minus x0 equals V0xt plus 1/2 AXT squared. And these two equations that we've derived, one of them for the velocity in the x direction, the other one for the displacement, or the change in x, they can then be combined to give us a whole host of special useful equations. And so, just to show you how these come about, when we have one-dimensional constant acceleration motion, we started off with this equation. We derived that. That's the equation for the straight line for velocity as a function of time. And then the expression for the area underneath the velocity graph, x minus x0 is V0xt plus 1/2 AXT squared. We can combine these two equations in several different ways and derive three new equations that can be very useful. So in the first case, we solve for t in the first equation and plug it into the second equation. And when we do the algebra and the smoke clears, we get this result. We get a result that relates the initial and final velocities along the x direction to the acceleration and the change in position. Notice equation 3 involves no time variable. So there are going to be problems where we won't know the time, and this equation may turn out to be useful. Secondly, we can take the first two equations, solve for ax in the first equation, and then substitute that into the second equation. I'm not going to show you the work, but I'll just show you what the answer is. This gives us equation number 4, and you'll notice that this is an equation that doesn't have acceleration in it. It's useful then in problems where perhaps we're not given the acceleration. And then finally, the third way of combining the first two equations is to solve for V0x in equation 1 and plug it into equation 2, and the result is that we will have an expression for the displacement x minus x0 that is related to the final velocity rather than the initial velocity. You'll see that equation 2 and equation 5 look very similar. The only difference is the velocity in equation 2 is the initial, and then in equation 5 it's the final, and there's a sign change in this 1/2 ax squared term. So we will have practice in class applying these equations to different kinds of one-dimensional motion problems. So here's an example that we'll do in class. I'm going to skip over it for now, simply because I want to now show the one additional special case of constant acceleration motion if an object is moving upward or downward in free fall conditions near the Earth's surface. So this could apply to a rock that's thrown straight up in the air or to an object that falls straight down. And we take these 5 equations that we've just derived and we can transform them into equations for the motion of objects in vertical free fall. And all we have to do is realize that we've got to change the x's to y's, because the vertical distance from the Earth's surface is usually regarded as the y direction, whereas the x direction would be the horizontal distance. So all of the x's will get changed to y's, and then anytime there's an acceleration, we'll replace the acceleration a sub y by this numerical value, which is negative 9.81 meters per second squared. It's negative because the acceleration near the Earth's surface is downward. G is simply a symbol that is used to represent this numerical value, 9.81 meters per second squared. So, just to show you how this works, equation 1 becomes the following, right there. Equation 2, the x's become y's, and ax becomes ay, which is negative g. Equation 3, equation 4, and equation 5. So if we have free fall problems, we will use these 5 equations here, and I just wanted to show you this so that you'd realize these are not new equations. They're simply the original 5 kinematic equations, but used in the special case where the motion is in the y direction and has the constant acceleration value that's shown here. So now we're ready to do some examples, and that's what we'll be spending class time on for the next few days. I'll see you in class.